The length of the beam is 89.1825 inches. What is the beam's moment of inertia in the joist position? This is important. The joist tells you which side is going to be the base and which is the height. And the joist is in the vertical position or the tall position, up and down. So we're going to have to use the long side as the height and the short side as the base. So if we put that into decimals, we can use the moment of inertia. I is the base times the height cubed, and that's all over 12. So if we put our numbers in here, our base is going to be the short side, 1.483. Our height is going to be the long side, 3.388. And we have to cube that, and then we have to divide by 12. So I use the parentheses to make sure we're dividing the whole thing by 12, so it looks just like the formula. And I'll leave that for you to put the numbers in. Here again, we're making sure that we're rounding to the nearest thousandth. So you need to put 3 decimal places in to get credit for your answer. And make sure you round, not just cut off the decimal. The next one, the modular elasticity, is given to us. They also give us the formula we can use for beam deflection. And number 2 says, what is the predicted deflection when 50 pounds are supported by the beam? So we're going to use this equation and put it into decimals. So the maximum deflection is F L cubed, and then we'll use those parentheses again to divide by 48. So I just like putting this in here so we can see the formula, and then we're going to use our mass. So we know that there's 50 pounds. We know that the length of the beam was 89.1825 inches. And we have to cube the length. And then we have to divide that by 48 times the modulus of elasticity. And here they tell us the modulus of elasticity is, how do we read this number? It's 1,728,000 psi. So we put that in here, 1,728,000. And then we also need to multiply by the I. The I will be the value that we've got in our previous answer here. So you'll have to put that in to get the right answer. And again, make sure that we're rounding to the nearest thousandth. So here they ask, number 3, what is the distance between the top of the caliper case and the beam? And so they show us the measurement here, and then they zoom in onto the caliper. So if we're going to look closely at that and zoom in, we need to read this off. So we can see here that we're more than 4, we're more than 5, we're past the 1, so it's going to be 5.1, and then we read the decimals off here. And you'll have to look closely and see which one this is closest to. So here's 5.110, here's 5.120, and it looks like we're pretty close right in there. So you'll practice reading that off and putting your answers in. Now they give the actual measurement with the weight. And so here again, we're going to have to read off, we're going to zoom in, read off that number, and then take the difference. So that would be the maximum deflection by subtracting the 2 height measurements. We do the same thing here for number 5, except instead of using 50 pounds, we're going to use 100 pounds. So if we go back to decimals, it's going to be their same work here, except all we have to do is change the 50 to 100. And then you can see how fast decimal could be to recheck your answers. And again, we measure the difference between the actual and the predicted value, and we tell how much. Now remember, this is the difference between the measured value and the predicted value. So the measured value, you're going to have to subtract the height of the beam from what the actual measurement is. You can find the original height of the beam was up here above when it's empty. So you're going to take the original height of the beam, subtract off the actual part, and that's what we put in here as the difference. And we're going to keep 50, and then again with So we got 25, we have 8 25-pound plates, and we're going to put those all in.